In this segment, we'll look at why one might want to introduce a new set of units on the atomic scale, and it basically boils down, like most things do, to experiments. Right? In doing experiments, or really just in everyday communication, it's always best to use the appropriate units. And these always seem to depend on the so-called scale of the problem, or the measurement at hand. The choice of units is generally always dictated by the human scale of thinking about a given problem, or the scale appropriate for the given problem. For instance, some kind of trivial examples. If I let W equal I'm doing a width of a standard size piece of notebook paper. Well, you can go and measure it with a ruler and find that that's 8.5 inches if you use the inches system. And that's a pretty standard thing that you'll see if you go buy notebook paper. They say, what size paper do you want? 8.5. I want the standard notebook size paper that's 8.5 inches wide, right? Uh, Now, it's not wrong. I can certainly convert inches to miles, and it's not wrong to call the width of that paper 1.57828 times 10 to the minus fifth miles. But the scale is totally inappropriate. Miles are good for much longer distance measurements, not the inches. On the alternative side, it's probably it's not wrong to say the distance from Edmond to Tulsa and give that value in inches, but it doesn't convey the information as quickly and as rapidly to people as you'd like. In fact, if you use the wrong scale, the wrong set of units, it really obscures things rather than makes things clarified. And so we don't want to obscure things. We want to be able to communicate clearly and efficiently. Yeah? So instead of using miles to measure the width of paper, we'd use more appropriate units, or inches or centimeters even. Yeah? Same thing for mass. Sometimes it's not the length scale. Sometimes it's the mass scales that determine various aspects of things. For instance, if you go and look around the NFL, the mass of a typical NFL running back is on the order. A typical mass is about 220 pounds, which turns into 100 kilograms. Okay? So the mass is 100 kilograms of a typical NFL running back. Well, the you know again, it's not wrong. I could express that in solar masses. It turns out the mass of our sun is about 2 times 10 to the 30 kilograms. And so I can certainly convert 100 kilograms to that. Yeah? But and express the mass of a typical running back in terms of solar masses, and everybody would think I was hopelessly pedantic or crazy if I started saying delineating masses and solar masses. Now, solar mass is not a bad unit if you're talking and trying to compare the mass of another star with the sun. For instance, another star might be 10 times the solar mass, and so you would write it as 10 solar masses. And that conveys a lot more information to people than even to use kilograms. So it depends on what you're measuring, what you're talking about. You want to convey the information as simply and as efficiently and as clear as possible. And that sort of dictates what set of units that you use. And the question for us is, well, what's the most appropriate set of units to use for the study of atoms? And the question is answered by looking at typical lengths and masses that are used when dealing with a system uh, of atomic systems. And that's how we determine it. We take a look at the problem and say, okay, it's more appropriate to use inches to measure the width of notebook paper, and it's more appropriate to use miles when I'm talking about distances from one town to another. Yeah. both measuring lengths, but one's more appropriate for one purpose than the other. And we do the same thing for atomic systems and study atomic systems. The atomic system, we look at the central players in it. What's the most important roles? Well, sort of if it were a movie, the lead actor in atomic systems is the electron. Electrons determine virtually all the important chemical properties of a substance. It determines the what reactions it will react with. It determines what how it interacts, whether there's an electron missing or something, how it interacts with electric and magnetic fields, and so on. So the electron sets two scales for us. One is the charge scale, and because it's 10 to the minus, the fundamental charge on an electron is 1.6 times 10 to the minus 19 coulombs. And it also sets the mass scale, which is 9.11 times 10 to the minus 31 is the mass of the electron. Now, it does this sometimes in sort of mysterious ways, or not, kind of is hidden. Remember, oftentimes you calculate the reduced mass, and for hydrogen and hydrogenic atoms, the reduced mass is just this expression. The mass of the electron is one mass, and the nucleus is the other, and it's given in that familiar form. But remember, the nucleus is some 2,000 times more massive than the electron, and so I'm not making much error if I just neglect this term in the denominator compared to 2,000, something that's 2,000 times more massive. That'd be like saying, well, it makes a significant difference what the mass of my car is if I have a baseball in it. The mass of the electron is about like a baseball, and the mass of the car is this. And so you pretty much can ignore the mass of the baseball if it's inside a car in terms of what the total mass of your system is. So if I ignore that in the denominator, then the two nuclear masses cancel out, and the reduced mass is very, very close to just the mass of the electron in these hydrogen and hydrogenic ions. So it's not horribly wrong to just, instead of using the reduced mass mu here, to just put in it's an approximation to be sure, but it is not horribly wrong to put in the mass electron. A lot of times you'll see people do that if they're not worried about things that are out in the third or fourth decimal place. So there's the Hamiltonian operator. If you look at that, that's quantum mechanics plays again a central role. And with the introduction of quantum mechanics, you had to introduce a new constant, a new physical constant, namely the quantum of angular momentum. And that's just Planck's constant divided by 2 pi, or h bar, and it plays a central role as well. And so in atomic physics, if I use our typical scale that we have in typical units, we see that all of these quantities are very, very small. And anytime something is getting huge exponents, exponential factors, 10 to the either a very large number or a very large positive number, or a very large negative number, then we probably need to be looking about using a different scale to measure things instead of our more traditional ones that are built around sort of a mean about the size of humans. In fact, they're all too small for an appropriate scale for atomic system. I'd like to introduce a set of units in which all these quantities don't have these huge exponentials with them, but have something close to integer, well, not integers, but small values, between 0 and 10 or so, maybe 50. So we need to introduce a more convenient system, more convenient for the study of atomic systems that have small numerical parts. And the numerical parts are these, and by probably small is not the right size, that are not so small. I don't want real large numbers or real small numbers, and in this case, we don't want such small numbers in this case. So I guess small is probably the appropriate word. Okay. Well, we'll see. There's well-defined techniques of how to do that, and we'll turn to that in the next segment.